Alright, so in this video I'm gonna be explaining another important article with the title Understanding Oversquashing and Bottlenecks on Graphs via Curvature. So this ICLR paper in 2022. Most graph neural networks use the message passing paradigm in which node features are propagated on the input graph. Recent works pointed to the distortion of information flowing from distant nodes as a factor limiting the efficiency of message passing for tasks relying on long-distance interactions. This phenomenon, referred to as oversquashing, has been heuristically attributed to graph bottlenecks, where the number of k-hop neighbors grows rapidly with k. We provide a precise description of the oversquashing phenomenon in GNNs and analyze how it arises from bottlenecks in the graph. For this purpose, we introduce a new edge-based combinatorial curvature and prove that negatively curved edges are responsible for the oversquashing issue. We also propose and experimentally test the curvature-based graph rewiring method to alleviate the oversquash. So as you see, it's a geometric problem and is very related to Ricci curvature in differential geometry. So sometimes the bottleneck doesn't let the random walk to efficiently explore different regions of your graph. And we should also distinguish oversquashing with underreaching. So message passing, we have an aggregation and update to go to the representation of the next layer. The hidden feature computed by message passing neural network with L layers is a differentiable function of the input node feature as long as the update and message functions are differentiable. The oversquashing of information can be understood in terms of one node representation failing to be affected by some input feature of node at distance or from node I. Hence, we propose the Jacobian as an explicit formal way of assessing the oversquashing effect. So, assume that message passing neural network in equation 1, if the gradient is bounded by alpha, also the gradient of update is bounded, gradient of aggregation is bounded, then you have this upper bound on this derivative. So it's good for understanding the sensitivity. So let's go back. This psi is related to update, the aggregation parameters, and also phi is related to the update function that we need to find. But it is saying that if we put the limit on the gradient of them, then we have a gradient, we have an upper bound on this, which is very nice. We are bounding the gradient. So, then the propagation of message is controlled by a suitable power of a hat. That's why in graph diffusion, generalized graph diffusion, this is an important factor. So we call it, for example, theta I a to the I. Of course, when I goes to a large number, then this should drop, this should go down. For convergence issues, also we don't want two distant nodes to be highly related to each other. And So you see different regimes of curvature. For example, for tree, we know that we have negative curvature. But click is a positive curvature, like an expander. But expander is not that much dense, so it's a middle between. And the grid has a zero curvature. So we propose a new curvature to address shortcoming of the existing candidate. And we use the following definition to describe the neighborhood of an edge and then they have this definition of Ricci curvature between 2 points, 2 nodes. So for any edge I and j, we can define the Ricci curvature. So it depends on the degree of each of them, are also these terms that we have defined in the previous slide. So this one, for example, these are the triangles based at ij. Or for example, forming a 4 cycle. Or gamma max is the maximal number of 4 cycles based at ij traversing a common node. So for C3 cycle, we have Ricci curvature of 3 by 2. Or for 4 cycle, we have Ricci curvature of 1. For complete graph, this is the Ricci curvature. So we are talking about curvature and oversquashing using this theorem. There is a bound on this. We have seen this fraction in other videos in this playlist. So you are familiar with that, which is very important for understanding oversquashing. Also, you know about Shiger constant and these classical thing in spectral graph theory, that the upper bound and we can upper bound, lower bound the first eigenvalue by those Shiger constants, which is a minimum of these values over any s that you define. And so if Ricci curvature is greater than k, it is a very interesting thing. It means that the Shiger constant, it means that the Shiger constant is greater than k. So if a Ricci curvature is too high, like a click, then it means that Shiger constant is greater than a k. And again, if you look at the definition, it means the number of edges going outside is too high, is a big number. So we expect, because in a complete graph, if you do a section like this, a cut, you see that the number of edges that go out is naturally a lot. So it makes sense. Even if you don't prove it, you understand that it makes sense. And the stochastic discrete Ricci flow. So negatively curved edges induce a bottleneck, like a tree, for example. It introduces a bottleneck because here could be dense, but the way that they communicate with each other is not dense. It's very sparse. So this, if you've given a graph G and a temperature, a number of iteration, an optional Ricci upper bound, then if you repeat it For example, for each edge with minimal curvature, calculate vector where this x and the improvement to Ricci curvature. So we are improving the Ricci curvature until convergence. So can random walk-based rewiring address bottlenecks? A good way of understanding the effectiveness of SDRF in reducing the graph bottleneck is through comparison with random walk-based rewiring strategies. Recall that the Chiger constant of a graph constitutes a rough measure of its bottleneckedness as induced by the intercommunity edges. Suppose we are given a graph with a small Chiger constant and we wish to rewire it into a graph G prime with a significantly improved Chiger constant in order to reduce the intercommunity bottleneck. A random walk-based rewiring method acts by smoothing out the graph adjacency and hence tends to promote connections among nodes at short diffusion distance. So such a rewiring method might fail to correct structural features like the bottleneck, which is instead more prominent for nodes that are at long diffusion distance. So the personalized PageRank matrix can be defined like this. So we rewire the graph using R with this kernel, meaning that we replace the given adjacency with R. Since R is stochastic, the new Chiger, remember this new Chiger constant is derived by R, not A, not adjacency. We have a better representation of topological features. So it's important to distinguish this kind of Chiger constant, which I haven't seen in any book or any article in the mathematical community. Maybe computer scientists are more creative, I don't know. So by applying it, we show that we cannot improve the Chiger constant arbitrarily well. And then we have this theorem that says if the volume of S is less than volume of G over 2, then the Chiger is upper bound. Homophily and bottleneck. So they tested on these Actor, Cora, Cicero, PubMed datasets, and you see this node classification benchmark. So shows the percent of edges added or removed by the method, because in rewiring we need to add or remove nodes or edges. So we introduce a new notion of edge-based Ricci curvature called balanced Forman curvature relating to classical Olivier Ricci curvature.